Hi. I decided to just have a donut. Bad timing. Anyway, welcome to East Portland. Haha. Almost at the end. I recognize everybody's probably end of the day, pretty tired maybe. So if you want to step outside, that's fine. I won't take it personally. I just do ask that if you want to have a conversation, try to keep it down. Anyway, so I work on Vyper, the language and the compiler. So this talk is kind of, wow, that's bright, is kind of for people who use Solidity, are experienced with it, wondering what else might be out there. So these are my handles on GitHub. I'm Charles-Cooper on Twitter. Big tech sucks. And if you follow me on Twitter, I promise you really great content like this, which I'll buy a drink for anybody who can figure out what this does within the next 5 seconds. It returns the data GM, encoded as a string. And so that's just, EVM stuff because that's what Vyper compiles to. So I guess I'll start out with a little bit of who is Vyper used by. So Yearn and Curve are both big users. I have some example contracts by them. So this is just a sample of what it looks like Python, hence the name Vyper. And in here, I'm getting ahead of myself, but you can see we've got a function that's external. You can call it from the outside world. And it does some math. It has some loops. You've got assertions, safety checks. Here is from the Yearn code base. We've got, this is an interface, so this is something you implement. So these are function signatures, and one thing you'll notice is all dynamic types, including strings, are bounded. So this is limited to 64 bytes, 32 bytes, and if you call it with more than that amount of data, you're going to get a reversion. That's important for reasons I'll go into. Here we've got a keyword arg, and we have Python-style doc strings. So that's just a sample. So I want to go into a little bit about the philosophy of Vyper, because basically that's what guides us when we design and implement the language, and maybe takes us in a slightly different direction from Solidity. So above all, we prioritize security and simplicity in the language. So if you go back here, everything is top level at the module. So if you can create a smart contract in, 2 or 3 lines of code that defines a contract. You don't need to have a keyword contract or entry points or anything like that. You just start defining your functions. So the language is supposed to be simple. It's also supposed to be auditable. We don't allow assembly. Basically, anything that could be tricky, we think a lot about in the design before we commit to anything. Other things that we do are bounds and overflow checking. So Vyper has always had safe math, and arrays are always checked, both the size and any kind of array accesses. It's kind of cool. So also loops, for loops, those are also always bounded. So you can always determine the upper bound on the gas usage of any given function, which is kind of neat because now gas limit attacks are not allowed by design. So you can write your contract and you can be pretty sure that it's not going to have a gas limit attack. Here's a few more features that I think are pretty cool about Vyper. Let me know if you have any questions. Feel free to raise your hand if you want to go into anything. I'm here. I'm trying to do this for you guys, so it's kind kind of interactive, maybe, if you want to like ask any questions or go into anything. So, so we've got some cool built-ins. So we have non-reentrancy checks are built into the language. I'll go into that in a bit. Safe math. We've got some math functions. So like a lot of people are coming from a Python background when they're like doing data science, and like a lot of people who do ML or whatever, they kind of expect math to be built into the language, and so we're trying to add math to the language. Vyper doesn't have any inheritance. Well, who here likes inheritance in Solidity and thinks it's really fun and easy to reason about? So anyways, Vyper, all contracts are basically in this kind of monolithic file style. We try to keep low syntactic overhead. All variables are stored in memory, so there's like not a 16 variable limit like there is in Solidity. And we've got bounded variables. And one thing that I'm really excited about is efficient code gen. So the EVM bytecode that we generate is pretty good. Some of you might be wondering, like, why isn't Vyper more widely used? And I want to address some of those things. Public enemy number one is dynamic arrays. So these are required for like compatibility with certain interfaces, certain contracts, like Uniswap uses dynamic arrays. And in order to be ABI compatible, we have to support that. Anyway, that's something we're working on and should be added in the next release or two. More integer types, ABI encoding, like the function was not in the language until recently. We don't have access to assembly, so like sometimes you really want to get around the language, and Vyper just doesn't allow that. It's by design, and so you basically have to ask us to add your use case to the language, which we're usually pretty good about, but you can't do it yourself, so to speak. And then I think the last thing is that there's like a historical perception that historically there's been a perception that it's like not really mature, that there's been bugs, and that was like maybe true 2 years ago, but in the last two major releases, 0.2 and V0.3, like the front end and the code gen has been pretty much completely rewritten, so it's like kind of brand new. Everybody good so far? Yeah. Great. Okay, so with all the philosophy out of the way, we can get into a contract. So, sorry? So we start out by defining a storage variable, a counter, and that's a hash map, and it maps addresses to uint256 in storage. And then we're going to define an internal and an external function. The internal function takes an address and then increments that address in storage. I don't know what you would do this for. It's an example anyways. And then we've got an external. I'm pointing on the. I should point here. So, and then we've got an external function, and we've got this modifier, non-reentrant, which marks it as a you can't re-enter this function. And then we've got the signature, and then it makes a call to self dot underscore increment counter. So it calls the private function. I want to go into this non-reentrancy thing a little bit more, because it's maybe not intuitive exactly how it works. So basically what you do is you use this modifier, and you come up with a key called foo, and you say, and that basically says, it generates this code actually. It allocates this foo thing to storage slot 0, and then as soon as the function is entered, it loads it from storage and checks that it's not set. And what would happen in a reentrancy attack is like foo calls out to some other malicious contract, and the malicious contract calls foo again, and because of this assertion, the whole thing is going to revert. because the malicious contract calls back this, and by that time we've already hit the S store 0, 1, and 1 is stored in the storage slot, and so like we've checked that we can't be re-entered. Does that make sense? Does anybody have any questions? Oh, hey. The question is, people who use Solidity are really used to importing safe math. How do we handle that in Vyper? Oh. So far, we've really taken the route of putting everything built into the language. So, like, people are used to importing safe math. Well, in Vyper, you just don't. It's built in. People are used to, like, importing ownable. Well, you use private functions for that. Does that kind of answer the question? And, like, non-reentrancy checks built into the language. OK, so most of this talk is actually just content I stole from Twitter. So a few days ago, somebody was optimizing this operation called fdiv, which is fixed point division in Solidity, and they dropped down to assembly. And they asked Twitter to help optimize it. And, you know, the Twitterverse responded with this. And I actually helped out with this a little bit. And then I was like thinking to myself, I wonder if Vyper is like competitive. So then I wrote this function in Vyper, which does the same thing. And this doesn't look like it has the same checks. Like this says like revert if y is 0, require all this, and that's actually checked for. In here, the compiler generates the safe math code to do the right thing. And then I was like, well, how does this compare? And actually, it does quite well. So the hand optimized Yule is over here, and this is what Vyper generates. And I measured it, and it's 33% more efficient, both in terms of bytecode and gas usage. And well, I can go into some reasons for that. But basically, because of the way Vyper is designed, first of all, memories are all allocated statically. So like, if you look at the entrance to the Yule function, the first thing it does is store OX80 to the free memory pointer. And in Vyper, we don't have a free memory pointer because everything is allocated statically. So you don't have to do that. There's a bunch of stuff in here which is like jumping around in the EVM code, and we don't have to do that over there. And lastly, one important thing is the ABI encoding. So whenever smart contracts interact with each other in Ethereum, they ABI encode and decode the data, application binary interface. And the code in Vyper is pretty well tuned, and this fact that memory is allocated statically also helps. So the section for ABI encoding is sorry. Where's return? Oh, it's right here. So it starts here, and then it's like 5 instructions to ABI encode that int. Over here, like the first thing that they need to do in Yule or Solidity is, locating, it's right here, is first load from the free memory pointer, and then like allocate stuff, and then push all this stuff onto the stack, and then return. So I'm not going to count this, on the spot, but it's several fewer instructions. And so anyway, so that's one thing I'm also pretty proud of is that, we have like really highly tuned ABI encode and decode. How am I doing on time? Here's another optimization we do is sequences of like if x equals y. This is like very common, is comparing things and then doing something because of it. So XOR is like a bitwise operation. For those of you who are familiar or not familiar, XOR of 1 and 0 is 1, and XOR of 1 and 1 is 0, 0 and 0 is 0. So basically, if two things are unequal, it will return something non-zero. And so so basically, XOR of x and itself, if x is equal to y, will return 0. So why is this faster? This looks like one instruction. This looks like 2. But this actually compiles because in the EVM, we only have jump I, which is like jump if not 0. And so you have to do these 2 instructions. You have to check if x and y are equal, and then you have to flip it, and then you have to jump to the end of the block. Whereas if you just compute x, y, and then XOR them, then it's like the opposite, but it's faster. And so anyways, so these are the kinds of optimizations that we do in Vyper that are like it's all of these added together. So you'll see checking the method ID, you've got push for this thing equals, sorry. Anyway, over here we've got the same thing except with a single XOR. Basically on this side there's an eq is 0, but I'm lost it. And then, yeah. And then another thing we do is now that we have all the safe math and we're like checking the results of arithmetic all the time, in this code we have like this sequence push 1 0 dupe 1 revert all over the place because you're doing a check, like check that a certain operation is in bounds, and then if it's not in bounds then you revert. So one thing we've done is like take all of those checks and push them into one code block at the end. And then in the code, we don't need to repeat this little block a bunch of times. And that, actually saves like 10% off the bytecode. OK. I think I might have bored you to tears already with all the optimization. Here's what's on our roadmap. We're going to do dynamic arrays. So I think that's a big blocker for people trying to use Vyper, and it's kind of the last blocker, and then it should be pretty much pretty usable. Another thing I'm really excited about is how we do encapsulation of functionality. So I mentioned before that Vyper contracts are usually monolithic. In the real world, people like to create libraries. They like encapsulation. And so basically, we've been thinking about this for a really long time, and we wanted to do something that's like really simple. And so basically, we have these kind of very restricted modules. So these are libraries that are planned. Basically, a library looks like a regular contract, but everything has to be internal functions and also pure. So it can't access contract storage or anything like that. And that way, you can like import stuff, and you don't have to worry about really what it does to your storage or anything. Like you're guaranteed that this is just a pure function, and all you have to do is read the code of it to find out what it does. But you don't have to worry about like a function override, like doing something to a persistent state that you didn't really expect. And so here's the tentative syntax, which is like you import this as this, and then you just access it kind of like a Python module, You just call the name of the module and then the function. And then how do we deal with encapsulation of like storage functionality? This is another proposal that we're working on. So here, so the concept is kind of like having an internal contract. So you create this file called linklist.vy in this case, and you import it as this, and this creates like a new kind of type. It's almost like an internal contract. And then you can create a storage type or a storage variable which has this type that you defined. And then you can like call functionality on this. And you can't access this underscore list variable. All you can do is access it through this functionality which you've defined. And so here at the bottom is basically a call to self.userList.insert, which calls this guy. And so that is like encapsulation of functionality related to storage. The idea is it's like a really strong encapsulation so that you can't just like modify the list variable however you want. You have to do it in the way that the library prescribes. And our idea is that that's kind of safer and maybe easier to reason about. Cool. Anyway, that is pretty much everything I wanted to, at a high level, everything I wanted to cover. I'm happy to answer questions. We always welcome people in our Vyper Discord. You can, chat with us. I'll be happy to talk with anybody who's interested in using Vyper in a project. And with that, I want to open the floor to questions or comments. Yeah, that's interesting. We have a function called, basically we have built-in support for proxy contracts. And I don't have examples handy, but I can chat with you afterwards about that.
I'm still trying to wrap my head around it. I think I got most of what you were explaining, but I think I need a better understanding of like what would make you choose Vyper specifically over Solidity, other than
Yeah, I think that I focused on that a lot because that's what I mostly spend my time working on. But Vyper is, in my opinion, generally easier to read. It's safer by default. So like up until Solidity 0.8, you had to like import safe math and like use it that way. Vyper's had it built in the whole time, so like we're really focused on safety and readability by default, if that makes sense.
so you would say like security is what focuses.
Yeah. We've really tried to design the language in a way so that secure code is like the default way to write things. Um, are you referring to Rust being used on like Solana? Yeah. So I think that in the future we're going to see, just for compatibility reasons, because Solidity and Vyper already have so much ecosystem like traction that like there's all these contracts already written for the EVM. And what we're probably going to see is like emulations of the EVM in Rust. So like Solana is going to have to, people like right now your options for building on Solana are like completely rewriting. And so I think that what people need to see in order to get more adoption of Solana is to have EVM emulators written in Rust so that you can take the same code and run it on Solana. And that like really reduces the friction. I mean, honestly, everybody is always talking about how, you know, Bash is like backwards compatibility with the EVM, but like there is a good reason for it, and it's like this moat, this EVM moat. And so we're really, I mean, we're really focused on optimizing EVM code, on targeting the EVM if, you know, uh, if we need to target more backends, that's actually something we're changing our architecture to be able to do fairly easily. But like for now, my perception is that everybody's like still pretty EVM focused. Anybody else? Great, thanks.